All right, cool. Thanks. Yeah, hello everyone. Thanks for coming to my talk, for the final talk here. My name is Sam. These days I work on the V8 security team, and in particular on a project called the V8 Heap Sandbox, and that's what this talk is about. Now, before we go into what the sandbox is and what it does, I want to kind of get everyone on the same page and start with this simple explanation of how a typical Chrome exploit works these days. So, you know, Chrome is like a big browser and has a sandbox, and a typical Chrome exploit chain looks kind of like this, like a exploit chain that starts with a V8 bug, I should say. And so, you know, you have a V8 bug at first. You need to exploit that to cause memory corruption. That memory corruption you turn into a primitive called arbitrary memory read-write. So something that lets you read and write all of the process memory. From there you somehow get code execution, like that might be shell code execution, might be return-oriented programming, might be job, whatever. Somehow you run your own code. And from there you have to break out of the Chrome sandbox. So you kind of need another bug, maybe in a privileged Chrome process, maybe in an operating system process. And then this kind of game repeats. You exploit this bug, and eventually you get unsandboxed code execution. Now, today what we're going to talk about is the V8 sandbox, and it comes into play in this part. So what it tries to break is this step from going from memory corruption to arbitrary memory read-write. That's what it's designed to do. Now, I guess you might be wondering, okay, why can't we, I don't know, fix stuff earlier? Can we not just prevent bugs or something? So let me talk briefly about that. So basically, why is JavaScript engine security hard? Now, this is clearly highly simplified, but I think it kind of makes the point. If you look at a typical application, whatever typical might mean, you kind of have a sort of stack like this, right? So at the bottom you have the hardware, then on top of that sit compiler and runtime, then is the code of the application, and then it processes some data. And that data might be attacker controlled, and so the code is the attack surface. But here in this scenario, the compiler is kind of removed from it. It's one level down, and so here the compiler could guarantee memory safety. So, you know, your code could be written in Rust or some other memory-safe language, and this works, right? However, in a JavaScript engine, the picture is a bit different. So really here, the attacker controls not just the data, but also the code, right? Because the attacker supplies JavaScript code, supplies WebAssembly code, and the compiler and runtime, they are directly part of the attack surface, right? And so in this case, the compiler cannot guarantee memory safety here because it's directly part of the attack surface. So any bug in the compiler is directly game over. So I think that's, again, simplified, but that's the big differentiation here. So to summarize, compiler-based memory safety doesn't work if your compiler is attack surface, because then any logic bug turns into memory corruption, and we haven't figured out how to fix logic bugs. Just as a kind of side note here, it's also not just about JIT compilers or so. So you can of course disable optimizing or optional compilers here, but that really just solves a part of your problem. It does attack surface reduction, so that's clearly good, right? But even if you turn off all the optional compilers, you still have a lot of attack surface and a lot of bugs. So that's not a full solution. And it's also very slow. So, yeah, to summarize, writing a high-performance memory-safe JS engine is hard. So kind of visualized, big problem, right? To do that, we would have to be able to write bug-free code, and we haven't figured out how to write bug-free code. Right, let's try something different, okay? So let's assume, or let's accept that memory corruption will happen, because bugs are going to happen. V8 has upwards of 1 million lines of highly complex C++ code, and yeah, bugs are going to happen. But instead what we want to do is we basically want to limit the memory that can be corrupted. And so we want to limit it to a certain part of the address space, and that's the V8 sandbox, or the V8 sandbox address space, right? And so that's a new security boundary resulting in an in-process sandbox. So let's build this from scratch, kind of walk you through how this is constructed. So we start by taking a huge chunk of the virtual address space. Currently, we take 1 terabyte of virtual address space, and like, in case you're wondering, like that's really cheap. Like on all modern operating systems, reserving address space is really cheap, so that's fine. So yeah, we take a terabyte of address space, and then really the interesting question is like, what objects do we have, and where do they live, and how do they reference each other? So, you know, these might be 2 heap objects, like 2 JavaScript objects, maybe something that your JS code operates on. So these live in the sandbox. That's like what we want to kind of sandbox. What's not okay is, like, let's say heap object 1 wants to reference heap object 2. What's not okay is for it to just point to it with like a 64-bit pointer. Because then if we have a raw pointer between these 2 objects, an attacker can just come, corrupt this pointer, and then kind of unlock the entire address space. So whenever you have a 64-bit pointer, an attacker can change it and then read and write anywhere in memory. They are not confined to the sandbox, so that's bad. So instead, all of these references, we simply turn them into offsets, right? So what used to be a 64-bit pointer is now, in this case, a 40-bit offset from the base of the sandbox. And now, if the attacker corrupts this offset, they haven't really gained anything, right? Like, they can corrupt this offset as much as they want. They still cannot address outside of this 1 terabyte. So that's like really, in short, the idea. It's fairly simple. Of course, we don't just have objects in the sandbox. We also have like external things. So, you know, in your web browser, for example, you have your DOM nodes, your HTML elements, whatever. Like, those are not V8 objects. They live elsewhere. But they do need to be referenced from V8 objects, right? So again, what's not okay is we cannot just reference them through a raw pointer. Again, the attacker can manipulate that pointer and unlock the entire address space. Now, in this case, we also cannot use an offset, so instead we use a table, right? So that reference turns into an index, into some table. This table has like some bit of type information and the real pointer, and then this is how you reference it. Now, maybe like if you think about it, this is actually relatively similar to how a modern operating system works. So you could think of the sandbox as being like the userland part, right? And that has like indices and stuff, and everything else is the kernel space. And any reference from user space to kernel space goes to some sort of table indirection. And like on Unix, that would be a file descriptor table, and on Windows, it would be like handles and stuff. So it's actually quite similar. But yeah, the basic idea: ban all the pointers. Pointers, bad. Get rid of those. Now, what I just described, so that's a software-based sandbox. This is purely, you can like do this purely in software, and that is what it's currently, what it currently is. And that's nice because it works everywhere. Like on every 64-bit system, you can run this. What would also be possible, and is something we would like to do in the future, is like a hardware-supported sandbox. And that effectively what that means is like as soon as you execute JavaScript code or WebAssembly code, you somehow like drop privileges. You execute some instruction that puts the CPU in some low privilege mode, and at that point, it can no longer like access any other memory. Like it's confined to the sandbox address space, and then it would be even more similar to this user space kernel split, where the CPU runs at different privilege levels. And I think really like ideally the point we would like to get to is we would like to basically take completely untrusted machine code and run it in our sandbox and be comfortable that that's fine. Of course, like we are far away from this, but kind of that's the goal maybe ultimately. Right, so what does this do? I think from my point of view, we saw that like writing bug-free code, that's a huge problem. We don't know how to solve it. In my opinion, if you take this sandboxing approach, you kind of break this big problem down into a whole bunch of like smaller problems that you still have to solve, but at least like they are maybe more realistic to solve. So that's what it does, I think. And what I'm going to do next is kind of walk through some of these problems that you encounter when trying to do this. So let's get started. I think the first thing that you have to, like the first problem you have to solve is this needs to be fast. So performance is really important. We want this to be like enabled everywhere, and it is. But for that, it needs to be like really low overhead. And I think here we are kind of in luck, because fundamentally these building blocks, they are really cheap. So like, for example, what I showed you with turning pointers into offsets, that's actually really cheap. You can see it at the bottom in like, if you're into ARM assembly, you can like, it basically does, that's the only change here. So what used to be simply loading a 64-bit value from memory, like loading the raw pointer from memory, that now becomes loading a 64-bit value from memory and then doing this like combined addition and right shift. So this add x3 thingy, that's like adding x3 to x28 and right shifting it first. And so the right shifting guarantees that we only have 40 bits, and x28 is the sandbox base. So really the cost of the sandbox here is one like constant time instruction, and that's very cheap. Like what's actually expensive are these pointer tables, because they require like one more memory load, like the load from the table. So that's basically where all of the overhead comes from. But yeah, it's still relatively okay. Like it's less than 1% today, and I don't think it will be much more. And you can compare this with other memory safety technologies that kind of have fundamentally more overhead. Like memory tagging has more overhead because it needs to load more memory on every access, like that sort of stuff. So I think this is kind of nice. We are lucky. So that's okay. Let's talk about some more like security problems you encounter. So yeah, you simply turning everything into raw pointer, like simply disabling or turning off all the raw pointers is not quite enough. There's going to be a lot more problems. One relatively obvious problem you will encounter is something like this, like code patterns like this. So you have some object, so that's in the sandbox, that's untrusted, and now from this object you load an index and take that index and go into some global array or some like out of sandbox array. And of course here the assumption is that whoever put this index into the object, at that point the index was in bounds, right? So like the index used to be fine, and this sort of code used to work perfectly fine without the sandbox. But now in this new attacker model, right, like an attacker can just come and corrupt this index, and then this access to the array goes out of bounds, and you have an out of bounds sprite in this case. So these are relatively trivial problems, like you find them by fuzzing, usually very quickly. Like you just have a simple fuzzer that corrupts heap memory, and then you see what happens. And this kind of thing falls out quickly. And it's also relatively simple to fix. I mean, like bounds checking is not a like hard science, right? Like you add some sort of check to this that the index is in bounds, and you're probably fine. And like this sandbox check, that's actually a thing. Like if you grab through the V8 source code, you will actually find like a lot of sandbox checks. They basically document that this is like important for the sandbox, and they make it possible to more accurately measure the overhead of the sandbox. So if you turn the sandbox off at compile time, these checks disappear. So it's more honest, basically. Now, I think in my point of view, like this is just part of a bigger group of problems that for lack of a better name, I'm just calling broken invariants here. I'll give you another example that's a bit more subtle. So this is something that also has happened a few times, or something like this. In this example, you have some like API function that returns you all of the property names of an object, for example. And it does this in some, like the way it does it is it first computes how many total properties are there in this object. It allocates an STD vector of exactly that size, and then it basically has to like process the different types of properties. So it first processes the like in-object properties and adds them to the vector, and then it deals with the others. And yeah, I mean, this sort of code exists, and it used to be perfectly fine. The kind of implicit assumption this code makes is that the number of in-object properties must not be greater than the total number of properties. And that sounds like a reasonable assumption. But now imagine that these like total number of properties and in-object properties, if these are just two integers stored in the object, then of course an attacker can come in, corrupt the like number of in-object properties, for example, make that larger, and then like this access to the vector goes out of bounds, and again we have some memory corruption. I mean, again, like this is not hard to fix, and actually, like right now we even, or by now Chrome has like the lib standard, lib C++ hardening turned on. So like std vector out of bounds access is already safe, basically. So yeah, these are also not super hard problems to solve, but there are quite a few of these issues that you run into when you like introduce a new security boundary. Yeah, let's talk about this one. So this one is, I think, in my opinion, the biggest problem we have with this approach. I'm just like, the best name I came up for is like Sandbox control flow integrity. You'll see why. Let's talk about the obvious thing. So clearly what you cannot do is you cannot have machine code in the sandbox. Like your JavaScript engine, it JIT compiles and it generates machine code. And if that machine code is in the sandbox, like you're going to have a bad time because an attacker can write to that. So, okay, machine code needs to go out of the sandbox, fair enough. Also kind of obvious, right? Like once it's out of the sandbox, you cannot reference it through a raw pointer. We discussed raw pointers bad, so no. So again, you need some pointer table indirection, and that already gives you like a form of control flow integrity. So now you're sure when you're calling into some piece of code, you actually land at a legitimate piece of code, right? A bit less obvious, you have similar problems with bytecode, because if you run like if V8's interpreter executes untrusted bytecode, then it can end up corrupting stack memory, and so that's also bad because the stack is trusted in this design. Again, move that out. I skipped one. So yeah, that's what I just said. The bytecode is bad, but also what's also bad, the thing I skipped is like there's code metadata in V8. Like there's metadata that describes how you, for example, relocate code from one address to the other or so. And if that's manipulated, that ends up corrupting the code, which then eventually is bad for the sandbox. So yeah. So these are a bunch of problems. I think it kind of ultimately boils down to the fact that this is a software-based sandbox at the moment. Like if we had this hardware-based sandbox, this would probably be fine because, like, as I said, the goal would be that we would be comfortable running completely untrusted machine code. So it doesn't matter if someone corrupts machine code. But yeah, we have a software-based sandbox at the moment, so all of this is a problem. So actually, like what the sandbox looks like, or what it looks like, what it really more looks like is like this here. We have not just one of these pointer tables, we have a few of them, and we have like different types of outside trusted spaces, and there's like code space that has the machine code, there's like a trusted space for like bytecode stuff. So yeah, things in V8 are rarely simple. So there you go. And yeah, there's still more problems in this area. So like even with what I just described, like there's still problems, for example, because you can mix up calling conventions or signatures. Like, could you imagine if you have a JavaScript call site that's supposed to call a JavaScript function, and it's probably bad if it ends up calling a WebAssembly function because they have completely different calling conventions and sort of that sort of stuff. So like that you need to fix. There's issues around like de-optimization and tier up. So in V8, like you have optimized machine code, but if something goes wrong, that can basically go back to like interpreted code, for example. But then you better make sure that like it's going back to the right code and not some other piece of bytecode, because then again stuff is mixed up. So yeah, like this is one thing where there's definitely more work needed, and I think that's where the most complexity is currently. Right, testing. So that's kind of a fun thing. So the sandbox is designed to be testable. Like for that, it basically needs a very clear attacker model, and it has that, right? It's like memory corruption in the sandbox must not lead to memory corruption outside. That's a very simple thing. And there's some tooling around making testing possible. And what it allows us to do is basically do automatic fuzzing. So there's some like fuzzers running that basically just corrupt heap memory and then monitor if like there's memory corruption outside of the sandbox. You can write regression tests. So actually in V8's like regression test folder, there's starting to be like sandbox bypasses being added. It's kind of funny. And I think most importantly, it allows this thing to be included in the bug bounty program. So just like I guess March, was it March? Yeah, or was it April? I don't know. March or April, the thing got included in the bug bounty program in like an early kind of early mode, I would say. And this requires us to like really have a clear definition of what's a bypass and how you can actually develop such a bypass. What you see at the bottom here is what we call our memory corruption API. So basically, you can turn on this API and it gives you the ability to read and write all of the sandbox memory. So you can create this thing called a sandbox memory view. You give it an offset from the start of the sandbox, so that's 0. You give it some size, and then it lets you completely read-write this entire in-sandbox address space. And that's basically what's emulating an attacker, right? Like that's emulating a typical V8 bug, and then this is used to write sandbox bypasses. So I actually do have a little demo. Let's see if that works, if I can get it to work. All right, let's see. Should probably make it a little bigger. How is this? Can you see this in the like back row? Excellent. Actually, let me start. So like this is this thing here, this like v-able enable memory corruption API. This is the compile time flag you set, and then you get all of this cool memory corruption stuff. And so yeah, then you build it, and demo.js is basically just what I showed, right? It's like constructing this sandbox data view, and then it's writing somewhere in the memory, the sandbox. Let's run that. So now what you have to do is you have to turn on this -- sandbox testing mode. And this is what, for example, enables the memory corruption at runtime. So let's run it. And so now you see, okay, we're in the debugger. This is in GDB. And we've caught a seg fault. Let's take a look what seg faulted. So we are at some place where it's like writing like the DL register to this address, and this address is of course oh, sorry, 6R8. Yeah. So right, like the register it's writing, the address it's writing to is like the base of the sandbox plus 41, 41, 41, 41, and there it caught the seg fault. So this is what you see in GDB. Now let's run this outside of GDB. And actually what happens now is, like, again, it tells you, okay, sandbox testing mode is now enabled. Currently we are a bit more strict, so we don't quite yet treat any memory corruption outside the sandbox as a bypass. Currently it like you need to demo like an arbitrary write. So it tells you, okay, please write to this specific page starting at this address, and then like that's how you demonstrate a bypass. But then it tells you down here, okay, it found where's my cursor? I don't know. Anyway, here, like it caught a harmless memory violation, memory access violation, because it's inside the sandbox address space. So what happened here is, with this sandbox testing mode, it enables also like a signal handler for seg fault, basically. And this signal handler for seg fault kicks in with the seg fault, looks at the address and is like, well, that's inside the sandbox address space, so that's actually fine. And I'm just going to exit here and say this is okay, right? Now I also have a different file here that I'm not going to show the content of, but it's called poc.js. And now if you run this, then you can see, okay, again, it tells you, please write to this address at this specific address. And somehow this file ends up actually writing to that address. And then you get a different type of crash. Now it says V8 sandbox violation detected. This is bad. We got a seg fault access error at this exact address. And yeah, that's how you demonstrate a sandbox bypass. Yeah, I mean, yeah. Yeah. I mean, thanks. I'm not sure how much of an achievement it is to like bypass your own security feature, but anyway, thank you. Okay, let's go back if I can find it. Oh no. Okay. No. Sorry, need to figure out the, yeah, there we have it. Right, that already brings me to the end. Conclusion, so I think basically what this ends up doing, like it increases the length of typical V8-based Chrome exploit chains by 1 bug, right? So no longer do you need like V8 bug and Chrome sandbox bug, now you actually need some bug in the middle for getting out of the sandbox. And I think really like the key question is, okay, how hard is this new attack surface? How hard is it going to be to get out of the sandbox? And honestly, I think the honest answer is like there's only one way to find out, right? Like you have to build this and then see what happens. And that's basically where we are at now. Yeah, because I mean, in theory, right? Like in theory, all of this works fine. Like the primitives work fine. Like everything's good in theory, but also in theory, you can write bug-free code. So, and in practice, that doesn't work. So, yeah, we'll have to see. But yeah, I have some more resources here. I mean, this is just if you download the slides later. And yeah, thanks for your attention. And I'm happy to take questions.
Hey. What's up, man? How much are you paying for the bypass?
Currently, we're paying 5K for it, and I'm hoping to increase that in the future.
Seriously?
Like, seriously, yeah. No, I mean, as you see, like, yeah, there's still a lot of work to do. So we are aware of quite a few issues, but yeah.
Thank you.
Sure. Please send us your stuff.
Probably a very naive question, but what happened, that first piece of code you had with the offsets, what happens if you feed in a negative offset?
So you mean the like in sandboxing where we use the 40-bit offset. So it's unsigned, it's all unsigned operations.
Oh, okay. Gotcha.
So basically like if you set it to a negative thing, it's still gonna write shift as a like biological operation, so it still ends up being like a positive 40-bit offset.
There goes my 5K.
Sorry. All right, cool. Yeah, I'll be around, so if you have more questions, and thank you.